right, thank you, Lucas. So, hi everyone, thanks for coming to my talk. This is thousands of virtual kubelets, one-to-one mapping a supercomputer to Kubernetes with Supernetes. Let's get started. So first, a little bit about myself. I'm Dennis. I'm a security and cloud computing master student at Aalto University here in Finland, as well as NTNU in Norway. My cloud-native career started at Weaveworks, where I am the co-author of Weave Ignite. And currently, I'm working on my master's thesis at the Astroinformatics Research Group at Aalto, with a focus on supercomputers and cloud integration. So let's first start with a quick poll to see which backgrounds you're coming from. First, raise your hand if you're familiar with high-performance computing or supercomputing on any level. Oh, wow, okay, we have quite a few. That's more than KubeCon. And then raise your hand if you're familiar with cloud computing or Kubernetes, again, any level. Yeah, that is to be expected for a KCD. Nice. So let's then hop in straight into some comparisons to get everyone on the same page. So on the highest level, the difference between cloud computing and high-performance computing is this. The cloud assumes infinite resources and finite demand, while HPC traditionally assumes finite resources and infinite demand. In practice, this means that cloud workloads are typically bound to a small set of nodes where there is node capacity for running a lot of these workloads in parallel. On the high-performance computing side, however, single workloads may span across the entire system, limited only by the number of nodes in total. And initially, this paints the picture that there are kind of fundamentally different assumptions at play when building for the cloud versus high-performance computing platforms. However, with the advent of especially artificial intelligence workloads, in today's market, the tables have turned for the cloud. Nowadays, cloud and HPC requirements look actually increasingly similar. The demand for resources by workloads is increasing, while platform limits are starting to show. Last September, the European Commission published a report by the former European Central Bank President Mario Draghi. Mario was tasked to prepare a report of his personal vision on the future of European competitiveness. In the report, Mario encouraged opening up HPC capacity to startups, small to medium-sized enterprises, and the broader AI community as a whole. He also highlighted the importance of expanding EuroHPC to additional cloud and storage capabilities, and also using unified public and private infrastructure for upcoming AI and cloud service deployments. To understand what all of this is about, we first need to understand the similarities and differences between the cloud and HPC worlds on an architectural level. So, modern HPC and cloud hardware is actually very similar. So let's focus on what differs between them, and that is specifically the software stack. As you probably know, most cloud platforms nowadays run Kubernetes, while a lot of high-performance computing systems run something called Slurm. And as a side note, for this presentation, I'm considering high-performance computing, its abbreviation HPC, and supercomputers to all to be essentially synonyms. So, reduced to their simplest forms, we can observe that Kubernetes and Slurm are fundamentally actually quite similar distributed systems. Let's start from the clients. These are the users of the system who interact with an API interface. Next, in both systems, we have a set of controllers which mutate the state. To keep track of that state, including, for example, workloads deployed by the users, both systems rely on a database. And finally, both systems have a set of node agents, one on each node, which handle the actual execution of the workloads. The main difference between the two lies in which components communicate with which other components. In Kubernetes, everything goes through the API server, while in Slurm, it's just a bit more complicated. However, even if the architectures look similar-ish on the component level, the high-level architecture is actually quite different, or let's say the goals are quite different. Kubernetes' strengths lie in its versatility and reconciliation. You can deploy Kubernetes basically anywhere, and its self-healing abilities make sure that the system keeps running through, for example, upgrades and partial failures. On the other hand, Slurm, as an HPC scheduler, has its strengths in scheduling large-scale multi-node workloads and optimally handling the complex hardware topologies that are present in modern HPC systems. On the drawbacks, Slurm definitely exposes a lower-level abstraction compared to Kubernetes, which currently has somewhat limited interfaces for hardware control. While the community is hard at work at improving the ease of deployment, setting up a Kubernetes cluster, especially at HPC scale, is still a rather involved process. I'll also highlight two key drawbacks in the Slurm ecosystem: multi-tenancy, particularly the security aspects of it, as well as high availability. Based on the experiences in my research group, the HPC software stack is much more fragile compared to Kubernetes, and for example, upgrades are not seamless. So, both sides have some key benefits, but also, unfortunately, drawbacks. What if we could merge the two communities and ecosystems, getting the advantages of both while minimizing their disadvantages? Around a year ago, this was the starting point for my master's thesis research. So, my quest to map the HPC and cloud integration landscape started on the Lumi supercomputer. Lumi is currently the 8th fastest supercomputer in the world and is located right here in my home country of Finland. However, through my exploration, I quickly gained the knowledge that Lumi is one of the trickiest supercomputers for this kind of research. None of the existing solutions that I tried would work, so the scope of my thesis suddenly expanded quite a lot. Introducing Supernetes. Supernetes is my master's thesis project that aims to bridge the gap between cloud and HPC. Supernetes is a so-called transparent bridge which connects a Kubernetes environment and a Slurm environment together. And crucially, Supernetes works on Lumi. Here's the architecture of Supernetes. There's a lot to take in, so let's do a step-by-step walkthrough of how this works. So first, you have a Kubernetes cluster on the top and an HPC environment, in this case Lumi, on the bottom. Supernetes itself consists of two components. You have the controller running in the Kubernetes cluster and the agent which is running on a login node in the HPC environment. The login node is essentially just an endpoint that you can SSH into. So first, the agent establishes a gRPC reverse tunnel, which is MTLS secured, to the controller. Then, the controller requests the agent to discover the nodes from the HPC side. For each node, one-to-one, the controller then deploys something called a virtual kubelet instance. This is essentially a virtual representation of a Kubernetes node, but without the backend part. So then let's say you deploy a pod. You can deploy it either directly through a job or by any other means, it doesn't matter. The controller then picks up your pod and passes it to the agent, which uses the Slurm commands to dispatch it as a job. In this case, that job is split into two tasks across two nodes. These new jobs then get observed, and pods will be created, and their status, logs, etc. bidirectionally synchronized on the virtual kubelet nodes. We need these, what I call shadow pods, since we can't split pods across nodes in Kubernetes like we can these Slurm jobs across multiple nodes in the supercomputer side through the use of these tasks. Finally, Supernetes then associates these created pods for the job with the original pod that you deployed, allowing you to see the status of the pod, the logs, and everything else, like your pod would be running natively on the Kubernetes cluster. And also, naturally, any other jobs running in the HPC environment will be observed and reconciled as well, leading to the virtual kubelet nodes in the Kubernetes cluster getting a complete view of the state of the respective nodes in the HPC cluster. This wouldn't have been possible without the great cloud-native GitOps tool FluxCD, or more commonly known as simply Flux, which I modified and integrated into Supernetes to achieve the consistent synchronization. And I'll also give a shout out to all of the work put into the virtual kubelet project, which is the backbone of how we mirror the entire HPC system into Kubernetes. All right, let's jump into a live demo and hope this works. Okay, Is it big enough? I think so. Great. So here on the top left, we have a view into my Kubernetes cluster. This Kubernetes cluster has 1,003 nodes at the moment. Of these 1,003, only one is an actual physical node that runs this cluster, and there's 1,002 virtual kubelet instances running at the moment, all managed by the Supernetes controller. If we scroll all the way to the bottom, we actually see that here's the only physical node that is currently running this cluster. On the bottom, I have a view open into Lumi. So this is a login node, which is just running the SQ command, so we can see any jobs dispatched with my user. And let's actually deploy a pod then. Or I'll actually highlight this small additional feature that I've implemented here. So Kubernetes is also able to gather all of the node metrics, or specifically the CPU and memory metrics of the nodes at the moment. And we can see that out of these 1,002 nodes, we have a CPU utilization of around 18%, which is quite low. And this is also one of the aspects that this work is aiming to improve. So let's check out the pod here. And let's make it a little bigger so we can actually see the whole thing. There we go. And this is just a regular V1 pod, nothing special about it. We can even use upstream containers. So this is just pulling the Alpine container from Docker Hub. And for live demo purposes, I'm just running a dummy workload, which counts to 300. This is so that we can get it scheduled quickly, because there's sometimes contention on Lumi. So we can't wait for a long time in the queue. And to actually get it to schedule on the Supernetes nodes, we need to specify a toleration so that it can be scheduled. And Kubernetes also supports, for example, specifying Slurm options through labels. So here I'm specifying an increased timeout so that this can finish running successfully. And now for this special case, I'm targeting this particular node that we will hop into over here to see it spawning. So let's apply it. And there we go. And now we see something maybe a little bit strange. So the pod is in the pending state. However, on the bottom, we see that it was immediately deployed and also immediately started running. This is what this R stands for. And this discrepancy comes from the fact that I need to poll Slurm. So it doesn't have an equivalent functionality to Kubernetes watch. So there's a bit of a delay here. And there we go. The 10-second polling interval expired, and now we see the shadow pod that was created. This represents this workload and maps together with the job ID, and also its state is now synchronized into your pod. And we see that this is in a special namespace, so if you would be looking at your workload namespace, the only thing you would be seeing is your own pod. And then we can have a look at the logs streaming in real time, like you would for a regular Kubernetes pod. And as a special addition for this talk, I will also show all of the current jobs that are being bidirectionally synchronized from Lumi. So there's 617 tasks represented as pods here. I hope people haven't put something confidential in the names of these. But yeah, there's a bunch of computation happening from various different users. Some of them pending, some of them completed, some of them running. All right. So, however, we're not done yet. As I've hinted, Supernetes is not alone in the HPC-to-cloud bridge landscape. Let's take a broader look at what's available. Here I've listed 6 projects that aim to bridge the gap between the cloud and HPC ecosystems. The first 3, namely Interlink, HPK, and Supernetes, are recently developed and also maintained. The next 3 are not deployable currently, but I've just listed them here for completeness. NOC is the predecessor of HPK and currently deprecated. Kfoundry was also presented at a prior KubeCon, but is still not public at the time of writing. And the Slinky Slurm bridge from SkedMD is yet to be developed. And take the last 2 especially with a grain of salt, since I've needed to make some educated guesses based on any public information that was available about them. So first of all of these solutions are able to take workloads, defined in some way or another, in Kubernetes and deploy them onto an HPC system. However, of these, only Supernetes is able to do the reverse, namely also synchronize jobs from the HPC system back into Kubernetes. Supernetes is also the only solution to provide a complete node view to Kubernetes schedulers by exposing the structure of the HPC nodes to Kubernetes. And finally, the firewall in place on many HPC systems, especially Lumi, is challenging for these bridges in general. And the yellow warnings here are not deal breakers, but might involve some additional setup, external components, or other workarounds. And for Slinky, this can't yet be evaluated. However, as great as Supernetes is, it also can't solve the two key HPC environment issues that I highlighted previously, the secure multi-tenancy and the high availability. In fact, none of the HPC bridge solutions can. So let me explain these two issues in a bit more detail. So first, the multi-tenancy. You can think of this like running a hotel. The tenants here are the customers that book rooms to do work in and store their stuff in. In this context, the tenants can, for example, be developers or teams from various AI companies working on different projects, doing training, as in training LLMs, and storing stuff in the form of training data and resulting models. At the moment, our hotel of Lumi needs to accommodate around 3,400 people. Let's see if that's feasible. In order to support multi-tenancy properly, the tenants must be able to be isolated from each other. In our hotel, we do have walls between the rooms. Directly accessing the data from other tenants is prevented through the use of Unix permissions. However, our hotel also has no locks to the on the doors to the rooms. So another tenant can just walk into the hallway of networking and directly access any other tenant's room where the other tenant might be, for example, running a Jupyter Lab environment. Through that environment, they can then access the stuff that the first tenant stored in their room, namely their confidential data and models. In technical terms, we don't have kernel nor user network namespaces. And technically, since we don't have process namespaces either, the walls between the rooms are also transparent, and you can see what all of the other tenants are currently doing, as you saw from the demo. On the Kubernetes side, there are existing and performance solutions for addressing these concerns. You can install locks for your rooms by taking advantage of, for example, network policies, Spiffy, and Cilium. Containers also provide us with opaque walls by default, since they isolate your processes. So let's next discuss the high availability concerns. Unlike the cloud, hardware faults and software upgrades in the HPC space often, unfortunately, involve downtime. This is a screenshot from my email inbox listing all of the issues with Lumi over the past year, where red entries are associated with downtime. So in terms of cost efficiency, let's do a bit of napkin math. Lumi has an allocated budget of 150 million euros, and a lifespan of around 5 years. So we can calculate an amortized cost of 30 million euros a year. That means the cost of 1 day of downtime works out to around 82,000 euros. These messages here involve an event of downtime that was continuous for 28 days. So first of all, imagine if like Google Cloud, AWS, or Azure would just go down like offline for a month for a software upgrade. If we take the same formulas, this works out to 2.3 million euros of essentially unusable capacity while the system is being upgraded. The successor to Lumi has already been allocated 250 million euros. And while we don't know the lifespan, it's safe to assume that it's probably under 10 years. So the cost of downtime will either stay the same or even go up in the future. So now that we understand these issues at hand, and that also bridge solutions aren't the ultimate solution, is there a way to unite the communities and ecosystems in an even better way? Let's board the seamless integration train to take a glimpse into the future. We'll start off at today's station. Today's station is our base case, namely how Lumi, for example, is set up today. It's just a single HPC environment jointly accessed by all of the tenants. So let's throttle up and off we go. From our base case, first we move the users up, and then we insert a new Kubernetes-enabled world in a new cloud environment. Now pay close attention. In order to retain the best parts of Slurm while avoiding its drawbacks, and also leverage Kubernetes strengths at the same time, the tenants now operate in isolated Slurm clusters running inside Kubernetes. This is actually nowadays already implemented by at least 3 projects. The Slinky Slurm operator by SkedMD, not to be confused with the Slinky Slurm bridge by SkedMD. And then we also have Sunk by CoreWeave and Soperator by Nebius AI. However, obviously, we still want to utilize the actual HPC hardware that is currently managed by the existing bare metal Slurm installation. This is where HPC-to-cloud bridges, and especially Supernetes, come into play. Supernetes aims to be able to expose the underlying hardware and Slurm installation to the Kubernetes cluster faithfully enough to support running HPC schedulers within the Kubernetes cluster. So essentially, it is a key component for essentially exposing a large enough Kubernetes cluster of sorts to evaluate the new environment atop the existing software stack and hardware. And with this, we've arrived at stopgap station. This marks a sort of intermediate checkpoint that is achievable today with minimal disruption to existing HPC customers and platforms. However, we can still go further. From stopgap station, we can now do something interesting. When we are ready to commit, Supernetes, together with the underlying bare metal installation of Slurm, can actually be entirely eliminated. And finally, Kubernetes can be dropped down to control the hardware directly. At this point, we've achieved our goal of combining the advantages of the cloud and HPC while minimizing their drawbacks. But why stop there? On the side, we've also gained the superpower to run the cloud-native batch ecosystem, including tools such as Kubeflow for AI and machine learning, as well as alternative HPC schedulers such as Flux Framework, and even completely custom pipelines. And thanks to various multi-cluster solutions, connecting this new hybrid environment to the cloud, or to an external cloud to say, is also no longer an issue. You don't need any more hacky bridges, and also there's no need to reinvent the wheel either. It's just a single, unified, and modern platform to build the future of supercomputing on. And with that, we have reached the final station. This architecture has a lot of potential. It empowers communities from both the HPC and cloud ecosystems to unify their efforts, benefiting all of the projects in the stack and making them more accessible to everyone. We gain improved security, better automation, broader ecosystem support, better utilization of the supercomputer hardware, specifically thanks to the accessibility improvements, and also reduced downtime and costs, just to mention a few. However, since I gave this presentation at KubeCon, another maintenance break for Lumi has been scheduled. This time, the whole system gets taken down for electric breaker maintenance. So how do we ensure high availability now? The traditional HPC software stack would be out of cards at this point, but the Kubernetes world has one more ace up its sleeve. Let's take a peek into how one would package an HPC application for this kind of Kubernetes environment. Unsurprisingly, the application lives in a container. The container might either be very minimal and serve just the application, or it might include stuff like development tools and libraries, including full runtime such as Slurm. Regardless, all of the HPC applications need at least a way to communicate across nodes and perform computation, typically on GPUs. To fulfill these requirements, inside of the container, the application links to client libraries for something called MPI, or Message Passing Interface, and your GPU vendor. Mind you that these libraries do not carry the entire MPI or GPU runtimes, which avoids container bloat. The runtimes themselves are provided by the platform. And in the case of Kubernetes, they are managed by operators that interact with each other. And ultimately, the operators are the ones to allocate the hardware resources. I'll also take this opportunity to clarify that there is no virtualization in this stack. Containers are a very lightweight abstraction. Once initialized, the runtime performance of all of these components is practically equivalent to running them on bare metal. Now, the crucial point here is this line, which separates the application from the platform. I call this the ABI boundary. Assuming you can maintain binary compatibility between the client library versions and the platform runtime versions, for both MPI and the GPU support, your HPC application container will be portable across supercomputer environments. The current track record from the vendors for this compatibility is not perfect, but it does exist both forwards and backwards, and importantly, it is usable in practice today. This means we actually have one more station ahead of us. Let's take a glimpse at future station. Thanks to the application portability, it is now feasible to network multiple cloud-native high-performance computing environments together, as is natively supported by the Kubernetes ecosystem. Applications can dynamically burst and be offloaded across the supercomputer mesh, and ultimately, we achieve the true high availability. An entire HPC system here can go offline without disruption to the users and workloads. So to conclude, we as a community need to start thinking about connecting HPC to the cloud today. Right now, we already have a set of HPC bridge solutions, including Supernetes, to act as a stopgap. And as we transition towards better solutions, we need to take care to improve the security posture and high availability of HPC in the process. And I also hope to have convinced you that Kubernetes is an excellent candidate for addressing these challenges. There's no need to reinvent the wheel, it's just a matter of the communities coming together for the greater good. Finally, if this presentation piqued your interest, hit me up. I'm working on finishing my master's thesis on Supernetes, and also I'm looking for interesting job opportunities to make this transition a reality. Thanks.
Great stuff. Questions for Dennis? There, right.
Hello, thank you for excellent talk. Kalle Happonen from CSC. Nowadays, an cloud admin for 10 years, but the next HPC admin. I think it's a very interesting and very good point to bring this closer, but I think this misrepresents a bit the downtime and availability of HPC systems. None of these are fixable by software, and that is by design. The design premise for HPC is very different than from cloud, and it's cheaper, because the system can be taken down, it's cheaper to design it so that it is going down rather than building hardware availability for everything. So I think even on the mails, like none of those downtimes were software. So I don't think you can maybe improve availability that much, but you can definitely improve integration and user, how to expose these systems to user in a more modern fashion.
Yeah, and that's also why I added the last part about making the portability a little bit more usable in practice as well, so we can potentially migrate the workloads before pulling the system down if there needs to be maintenance done for the system, for example.
One other question? Where is it?
Hey, thanks for an excellent talk. So I also had a kind of thought on the high availability, describing the community effort and the kind of collaboration to do this job. But there's the HPC infrastructure is owned by large companies and paid by governments. So I'm just thinking that might be a problem with the HA. So how would you address that?
Yeah, like mentioned, it's not that big of a technical problem to make this happen. It's more of a kind of, societal one. We need to start thinking about these solutions when designing these platforms. And there's a supply chain involved with these systems, and software components and hardware components are gathered from different vendors. Most of the software stack is already using open source software, but it's also about meeting user expectations. So the users that use the HPC systems, like Ricardo's great talk mentioned, the keynote in the morning mentioned that they still want their SSH access and stuff like that. We need to sort of adopt those practices without breaking backwards compatibility here. And that's where it's all starting, and slowly change out the components and try it out. And like you mentioned, yes, these large companies and also the national supercomputer operators need to be willing to start trialing these concepts. So it starts from there, really.
Okay, thank you.